Yes, good morning. This is Shivashankar Rajamani from KSR College of Engineering, and we are celebrating our 25th year of academic excellence. Today, I will be handling about optical fiber communication subject. In that, so I will be taking about ray theory, which is the important thing to understand optical fiber communication. Ray theory, we generally call it as geometric optics. So, since it is related with light energy, it's called as geometric optics. And this is my content page, introduction, basic principle which is being used in optical communication, then comparison of various refractive indexes of different materials, then ray theory, how it works, then partially reflected wave, how it works, then critical angle, then total internal reflection, comparison of electronic and optical communication. This is my content. Introduction. It is the method of transmitting information from one place to another by sending light through a fiber, optical fiber. Here the transmitter will be a light source and the receiver will be your photodetector. In between the communication will be your fiber. That's why it's called as optical fiber. Since the fiber is used to insert light inside the fiber, so it's called as optical fiber. The light from the electromagnetic carrier wave that has been used to carry information with the help of modulation. Here the light will be in the form of electromagnetic, both electrical as well as magnetic. In general, electronic communication, it deals with information in the form of voltage and current, whereas optical communication will be in the form of light. That is the main difference between normal electronic communication and optical communication. We will see the comparison in the last slide. Then basic principle. So light consists of both waves as well as particles. When you see deep into the light, so it has a small thing which you call it as a photons. Sometimes you could able to see the photons as a particle, and the particle will not stay at a place. It will just traveling in the form of wave. That's why light consists of both wave as well as particle. Here we will be dealing about ray theory, that is how a Snell's law works. Then if you want to find how this light behaves as a wave theory, for that you need to have a basic knowledge of electromagnetic theory. Then if you want to see the as a particle, that is light as a particle, you need to have a strong knowledge of quantum theory. Nowadays quantum theory says about qubits which can move in upward direction or downward direction, which is a superimposed particle and well as tangible particle. Here you need to have a strong knowledge of quantum physics, so that in order to understand the quantum as a particle. Now we'll see about our subject, a basic principle. Light is a transverse electromagnetic wave that can be seen by human eye. Right, so when a white light is being transferred through a prism, you could able to see the 7 colors. Right, so that can be viewed by human eye. If it is infrared or ultraviolet rays, we could not able to see that. So light travels faster in vacuum with a velocity of 3 into 10 meter per second. The velocity of light gets reduced in denser medium. When light is moving in a vacuum, it will be in the speed of 3 into 10 meter 10 power 8 meter per second, whereas it's moving in the denser medium, the speed gets reduced. The speed of get reduced by 3% in air, that is above the ozone layer, then 30% in glass, so that has to be defined by a refractive index. So refractive index is defined as the ratio of velocity of light in vacuum to the velocity of light in any medium or denser medium. It's a ratio. So refractive index, it's generally represented by n, which is equal to velocity of light in vacuum divided by velocity of light in a denser medium. Denser medium may be a the water or any metal or fiber or plastic, whatever it is. Right, so we have a comparison of refractive index and the material used. For vacuum, we assume that refractive index is 1, that is numerator and denominator is same. Whereas for air, the light is little bit, find it very difficult to travel inside the air. Right, it is in the order of 1.000277. Whereas in water, the refractive index is represented as 1.3333. For ice, the refractive index is given by 1.31. For glass, it will be ranging depending upon the impurities being added in the glass fiber. If impurities are more, so it will be in the order of 1.45. If it is impurities are less, it will be in the order of 1.5. So that will be a refractive index. Here for our optical fiber communication, we will be using either plastic fiber or a glass fiber in the order of 1.45 to 1.5. For diamond, the refractive index will be, it's 2.417. That is, light travels very difficult inside the diamond. That is the thing that I want to convey. Then ray theory, when light passes from one medium to another medium, cause a change in speed which result in direction of light. So when a light is been sent from a lighter medium to denser medium, when light travels in the denser medium, it will not go straight, it will just move away from the normal. And that is called as deflection of light, which is called as refraction. The law of reflection says that angle between the incident ray and the reflector ray are same. That is, theta I is equal to theta R. In other words, we can say that angle of incident is equal to angle of reflected ray. First, we will see about how the partially reflected wave works. So I have a two medium. So N1 is a lighter medium and N2 is a denser medium. So I am just sending a signal from lighter denser medium to a lighter medium. So the light at theta is moving away from the normal, it is not a straight line. Half of the light will be get reflected, that is called as partially reflected wave. This partially reflected wave cannot be used in our optical fiber communication. We need to have a fully reflected wave, right? So half of the wave has been refracted inside the denser lighter medium. So case 1, which is called as partially reflection, here we will be using this Snell's law to prove that. Snell's law relates between the reflected ray light and the incident light. N1 is the refractive index of the lighter medium and N2 is the refractive index of the denser medium. So N1 is greater than N2. So angle theta 2 will be more than theta 1 as the time they travel will be reflected into the lighter medium and partially reflected back into the same medium, which we call it as partially reflected ray. The remaining light will be refracted into the medium. Here we could able to see that the angle of reflection at the interface of two material is given by Snell's law. So N1 is the refractive index of denser medium and N2 is the refractive index of lighter medium. Here we could able to see that light is moving away from the normal, right? So we are considering that N1 is greater than N2. That is the condition, right? So N1 is act as a water. So water, its refractive index is 1.333, whereas N2 is refractive index is 1.000277. Here it is, this ray you call it as a refracted ray. So it's given by Snell's law, N1 into sin theta 1 is equal to N2 into sin theta 2. So N1 by N2 is equal to sin theta 2 divided by sin theta 1. So this is called as a refracted ray when a pencil or a pen which has been inserted into a beaker which contains water. It will not be in a straight line, it will be just bending. This is called as refraction of light. Then second is your critical angle case 2. Here N1 is greater than N2, where N1 is your water medium and N2 is your air medium. When the angle of reflection is more than 90 degrees, so I am just increasing the angle. So reflected ray emerges parallel into the interface between the dielectric. When the angle theta 2 is 90, it is called as critical angle, and it is represented by theta c. It is the limiting case of refraction, and the angle of incidence is known as critical angle, and it is represented by theta c. So the Snell's law becomes as N1 sin theta 1 is equal to N2 into sin theta 2, where theta 2 is 90 degrees. So if you want to find the critical angle, it is sin inverse of N2 divided by N1. So the minimum angle of incidence at which light ray strikes of two medium, which result in the angle of refraction of 90 degrees, and it is goes parallel into the interface. Then last is your total internal reflection. So the first condition should be N1 should be greater than N2. Then second condition, theta 1 should be greater than your critical angle. That is the condition. So we have two conditions. First condition, N1 should be greater than N2, and second condition, theta 1 should be greater than your critical angle. So if you use this, so this ray will reflect, which you call it as totally internal reflection into the same medium, right? So reflected light does not exist, only light will be totally reflected back into the same medium. Here it is material 1, that is water. Here the condition is theta is much greater than your critical angle, that is the condition. So this is Snell's law. So it's N1 is equal to sin theta 2 divided by sin theta 1. And this is the total internal reflection. This is the basic condition to understand the light will be traveling inside the fiber. So fiber has to travel a long distance. So light has to travel using this total internal reflection. So the light will be inside the fiber. It will not go out of the fiber. Even then, if it goes, that will be considered as a loss. So we have sent two signals, light signal 1, which is represented in blue color, that also goes total internal reflection, and light 2, which is also as the total internal reflection. Now we'll have a comparison of electronic communication and optical communication. Information in the form of voltage and current is in the electronic communication, whereas information in the form of light. If it is 1, we will have a light. If it is 0, there will be no light. Then here it will be study about electronic devices, circuit components, whereas here you will be studying about source, detectors, and fiber needle. Wire and wireless communications possible. Here it is only wired communication is possible, but to a long distance. The electronic and electric circuit components and electromagnetic theory concepts are needed to understand. Here optical ray theory and electromagnetic theory is need to understand. Thank you. I need your feedbacks and suggestions in order to improve my